That works. Better?
Yeah, good.
Yeah, that's it. Okay. Okay, sorry for the technical glitches. And so let me just get to the topic here. My topic is called make every bit of bandwidth count and workload acceleration in the era of AI and cloud. So I want to set up a little bit of context here. When we talk about the workload acceleration, right? Workload means the programs, the algorithms, right? And our models, the one we want to run on the computing infrastructure. And at the high level, you can think of these two approaches, right? One is you optimize your workload for a given computing infrastructure. So which means your computing hardware is given to you. So you optimize your workload. The other one is you know a set of workloads. You try to optimize your computing infrastructure so your workload can run better. Right? That's kind of the two approaches. And of course, in between, you can say always do the co-optimization, as like yesterday, some of the speaker mentioned, right? You can do the co-optimizing of your workload and your infrastructure. So which means you change both your algorithms and your infrastructures to optimize your overall, whatever the metric. And so of course, there's many works in this all this kind three areas. And I also have some work in all of these areas too. But today's topic will be only focused on the first one, which means let's assume the workload is given to you and how are you going to optimize your workload. And speaking of the workload, and let's take, and by the way, I'm not going to give you the introduction of why this AI is needed, why the cloud is needed, okay? I assume this is a given. And so given the workload, let's see, how traditionally we try to account for the complexity or the whatever the metric, right? The difficulty or the computations, and how do we account for this workload? How do we measure it? And a typical metric is this complexity, right? I think anyone with the computer science background, this should be kind of very obvious. You heard of this many times, right? And asymptotically, we have this either in terms of the time, means the performance, speed, right? And the complexity, and or in terms of the space, the memory, right? The storage. And this is space complexity. And we have different levels of complexity, and be it linear or quadratic or constant, right? Or even exponential. So we always try to optimize your workload or somehow make sure that your complexity is manageable and as your input grows, right? And that is very typical. But if we look at it traditionally, right, because of our computing infrastructure, this kind of complexity concept that has been devised by the computer science many years ago, and that was based on actually kind of some assumptions of the computing infrastructure, right? In the old days, of course, it's only a single core computer, right? And the CPU, and this is a very kind of famous Neumann architecture, right? You have the CPUs, you have the memories, and you have the IOs, and you need to move your data from the memory to the CPUs to do the computation. And traditionally, the CPU is in old days, right? It's a single core, right? It can only do one thing at a time. And so your data movement is not a big issue. So you just move in and you crunch your data. Even you have a lot of data, anyway, you have only one unit of computing, right? So that's when you just, it's typically computing bounded. So, and the data movement, the cost, etc., is not such a big deal, and everything is relatively slow. And so that's kind of the concept behind the complexity. And people have tried to use that complexity to measure, right? Like how good is your algorithm, right? Because that kind of measures your performance of your algorithm in terms of complexity, right? The time complexity or space complexity. And if you design new algorithm, you always say, hey, this is my complexity, it shows how good you are. But things has kind of started to change, right? Especially in the era of AI and clouds. And so talk about AI first, right? So we know the AI workload has changed dramatically, because of probably it's kind of overbloated the term. The AI means sometimes it's bigger data and a lot of data analytics. You need to have a lot of data, right? And of course, some of this neural network and some of the particular workload, because you need to deploy it onto the cloud and a lot of the applications in the cloud, right? For example, like a Google, some of Amazon, for example, right? Or the Netflix or YouTube. There's a lot of big recommendation systems. That's kind of one of the largest models and deployed in many bigger commercial side companies. And you still have to crunch data, the big data, right? And a lot of this relationship, like yesterday is one of the talk, right? It's about a lot of the connections is through the graph, right? It's a better way to capture the relationship. So there's a bigger graph analytics. And of course, now ChatGPT or the transformers or large language models. So these are all new workload, right? That requires much more heavy computation, requires many more storage or the memories to store your data and store your larger models. So this means your traditional computation is not enough. That's why so-called accelerators, right? And it becomes more widely used. So you need more accelerators. So what do we mean by the accelerator? So let's just kind of take a look, very simple look, right? The accelerator, you can think of, I'm broadly define this one, right? If you look at the CPUs, the cores, right? So you can see there's even more number of cores in a single CPU, right? And of course, talk about some of the other accelerators, one of them is NVIDIA, so like a GPUs, right? There's even thousands of cores. So which means the computing, right? Getting the parallelized computing becomes more and more powerful, right? You can do more computation now. And that's why, this is becomes, I would say the trend has been for the past decades. And that's starting to shift, right? The computer bound to the so-called memory bound or the bandwidth bound. To understand this a little bit more why, right? And so we can show you later, why this is the case. But if you look at this in the cloud AI, if you try to deploy the computing infrastructure, in a sense, and this is kind of how it will look like. You have the cloud, you have many, many nodes. If you zoom in a particular node, right, on my right hand side, right? So you still have a traditional CPU, you still have your memory, you still have these connections, right? But now you have to, through the PCIe, for example, switches, you attach more accelerators, right? Which including the GPUs and accelerators, not only GPU, right? Can be other type of accelerators too. For example, like FPGAs and in terms of memories, right? And now the SSD, right? And also to also attach to the system. And through the connections, you have other workload, right? And the workload is the same kind of a server node, or can be even including high performance computing, or maybe even future in the quantum computing. So this is the kind of a general view. You can see this is really the trend of the industry going in terms of the infrastructure, right? To support the emerging AI workload. So now let me go back to the point I mentioned, why I think the system is moving to this memory bound and the bandwidth bound, right? And this is kind of a very simple illustrative point. And thanks to my collaborator, Professor Wei, he made his slides a few years ago, so I can reuse his slides. So he's using the Volta GPU as an example to show what are the challenges, right? On the one side, this green one is a GPU, for example, right? Your GPU is, hey, what is the flops, right? This shows you, okay, how many 14 kind of teraflops per second, which means you need to do so many floating point computation per second. And then you have the memory bandwidth, right? Which access the, in this case, the HBM, getting the data from the memory to your computation. You need to say, hey, I need a higher bandwidth. This one is 900 gigabytes per second, right? It's from Volta. But now think of this way, this is the infrastructure given to you. How are you going to design your workload to optimize the system? Meaning, how are you going to utilize the system as much as you can? So let's assume, right? In order for me to fully utilize my computation, like the GPU, the teraflops, you need to put a pump the data, right, from the memory to the computation. But this was very simple back of the envelope computation. You will realize actually it's very interesting. For example, now you have this memory bandwidth, which is 9 gigabytes per second. Let's assume we are using a single floating point computation, which is 4 bytes per floating point, right? So which means every second, you can pump how many floating points into the system, which is about 225 gigabytes, right? And a gig kind of single floating points per second. Now you have so many computation, which is teraflops per second. So now you think of every operand you pump in. If you want to keep all the computing units fully utilized or busy, which means very simple, right? Back of the envelope computation. every data you pumped into the computation need to be reused about 42 times in order to keep everyone busy. Okay, if you only move in data, use it once, out of so many computing units, only 1.6 will be busy. The rest, 99% almost, is quiet. So what's the challenge here? You can see, right? Either you have to design algorithms that can pump the data, reutilized about 42 times every time, or you have to keep a lot of the computer units idle. So that shows you, right? Even though you have this infrastructure, you try to make system every piece to work, keep everything fully utilized, keep everything busy or balanced. It's very difficult. Why? Think of any algorithms you have. What kind of algorithm you can design that can utilize every operand that need to be reutilized about 42 times. The famous one, right? The matrix multiplication. You only access it once, you utilize only once. Right? That's the biggest workload almost, right? All the accelerators try to accelerate the GPUs, or try to accelerate the work, the matrix multiplication. That's what I mean. Very, very rarely, right? A program, a workload can sustain such a high data reuse. So which means the computer, actually, now that's when if your reuse rate is not high, actually your computer actually mostly stay hungry for data. And that's what really is the reason, main reason why this is a memory bound issues. Right? That has been talked about in many, I say, probably a lot of the recent computing conferences. You hear this a lot, right? I just give a different kind of more simplistic kind of explanation, more intuitive way to explain why it's so. That kind of really drives industries, right? I would call it insatiate quest, right, for more bandwidth. That's why you look at the industry, right? Look at the industry. Right? You can see on the one hand, right? This is kind of this data is a little bit old, right? It's stop at 2018, but it's a similar trend. On the left-hand side shows you the CPU or the computation capabilities. It's exponentially grow, right? Which means people want more and more powerful computers or servers, right? That you can see this gigaflops per second, right? Keep increasing. That's on the one hand. On the other hand, if you look at the memory bandwidth, again, it's keep increasing exponentially. Like you can see, even NVIDIA's latest H100 GPUs, right? Just keep increasing the memory bandwidth. This seems to be very norm, right? People say, hey, this is the right way to do. But given the principle, given the phenomena I just said, is that really true or not, right? Is that really a good strategy? Because it's, as I just simple computation showed you, it's very difficult for us to fully utilize the current given resources, right? Be the compute or the bandwidth. So that's what I mean. Even though there's a need for more bandwidth, right? But do not try to make that to be an easy excuse. We always say, hey, let me buy more powerful machine. Let me buy more the machines or design systems that with more bandwidth or more memory, whatever. That I think is a poor strategy, right? Because you are not trying to really optimize your workload. So this is kind of the essence of the talk, right? So I think it's a workload optimization principle, what it is, a simple principle, right? Let's try to make every bit of bandwidth count. And I'm going to use two examples to illustrate this one. And how can we achieve this one? Okay. So here I just a few like servers, right? And that's commonly deployed, right? It's as you can in the cloud, most cloud vendors will support a different type of servers, and sometimes they try to be uniform for ease of management. But different cloud vendors will have different systems, right? Here, just show you a few. Okay, so, because my history is from IBM, so I showed you a few IBM servers. But it doesn't matter which generation of the CPUs. It's similar, right? You have some kind of the CPU cores, you have the GPUs as accelerator. Of course, now Microsoft has the FPGAs, etc. But similar, you have some kind of interconnect or connections, right? To connecting those computing units. And the computing units can be the different type of the link, right? You get the NVLink, different version of NVLink or the PCIe links. and it also has different topologies. The point is, first case, as you can see, different server system designs, right? This connection is quite complex. And every connections in terms of the so-called the nominal values in terms of bandwidth, right, is different. And of course, computing capability is also different because different servers, different CPUs, they're different. Now you try this given infrastructure, you try to optimize your workload for the such kind of infrastructure. What you should do, right? So let me zoom in a particular connections. Let's say you have the CPUs, you have a GPU. This is very typical right now, right? In the cloud. And so now you have the CPU on the one side, you have the GPU on the one side. The CPU has its CPU's memory, and the GPU has its GPU's memory. And there's a different ways of moving data from the CPU side to the GPU side, right? And the CPU can do the computation, GPU can do the computation. This, as you can see, this is kind of from NVIDIA's CUDA programming kind of book, right? You can see this, in order for you to transfer data, there's different ways. You have the pageable data transfer, you have the pinned data transfer, you have the zero copy transfer. These are the three major type of the data transfer, right? It's a physical and how they do the implementation. There's also logical ones, now the NVIDIA promote is called the unified data memory. So which means from the program perspective, you just assume the memory, right? From the CPU, from the GPU, is logically it's kind of one, right? And let the NVIDIA's drivers to manage this data, actually physically still have separate CPU from the memories and the GPU memories. And there's different ways of doing the programming. And for the workload, you have to use this kind of mechanisms. And out of those many options, like the first two, right? Like this is a pageable data transfer, and the pinned data transfer, in a sense, it's the bulk data transfer, right? Which means that you kind of pin your data, and when you do the computation, you do the bulk DMA kind of transfer. That's how you utilize your bandwidth, because of the fast DMA utilization. The zero copy means it's from the GPU side, you on demand get your data from the memory side, from the CPU side. And in terms of programming simplicity, right, you will think of the zero copy data transfer is the simplest one, because that's kind of on the GPU side, you on demand get the data from the CPU side. But unfortunately, this is a very simple programming model in a sense from the CPU, zero copy data. If you look at the conventional wisdom, or you look at the recommendation, even from NVIDIA, right? People feel, okay, the zero copy is a poor performance kind of a programming model. And from both the recommendations and from the academic papers, people feel like this is a poorly way of moving data. And why? Because when you try to get your data from the GPU side to the CPU side, right? If you on demand get the data need to be transferred from the link, right? Which is the PCI link in this case, for example, or in NVIDIA case, is the NV link. Because the link is the kind of the relative have the fixed bandwidth, and that's hey, this is you cannot be very performant. And this becomes a common wisdom, right? But unfortunately, if you look at it deeper, if you realize actually there's no systematic study or there's no convincing story of why it is so. Okay. And so let me kind of make this more concrete and kind of give you some ideas how this is tied to the workload, right? So now, and in this AI, one of the very common workload is called the graph neural network, right? The graph neural network is you represent your data into the graph, and then you use the kind of the graph neural network to apply to some kind of the representations of the node or the edge. Based on representations, you can do the recommendations or you can do the classification, whatever. So this is kind of the why the graph neural network is getting a lot of attention, right? And one of the way to do the graph neural network is which means you have to operate on your graph. And the way you do the graph neural network is you can think of this as a very high level, simple three operations, right? You pick a particular node, you look at the neighbors, you randomly sample your neighbors, right? You get your information from your neighbors, you do some computation, becomes your representations, and you keep doing this for many different nodes. That's kind of the graph neural network at a very high level. And this is one of the largest, probably one of the largest computation workload in the cloud for the AI. And because of your data is big, right? In a lot of data, and GPU memory is limited, so you cannot fit all the data into your GPU. So which means you need to utilize your CPU memories to make sure this work. And that's how it was utilized, designed right now. And but because you have the graph data structure, so I don't know if how many of you know there's a graph data structure here, right? For example, you have a graph, like this node 1, 2, 3, 4, 5 is a node that have connections, right? And this data you need to have some compact representation. One of them is called compressed sparse rows. So this is kind of show in the bottom, right? Like you have the vertex list, you have your edge list, right? And you do the representations. So this kind of shows you in order for you to traverse your graph, you have to jump around in the memory. So that's amazing. As you know, the memory access, right? If you're jumping around the memories, this is because the cache effects, that is very slow in terms of performance. So this kind of shows the challenges for optimizing the graph operations on the GPU. And one of the most popular frameworks, right, for people to train the graph neural network is DGL, for example, like a PyTorch DGL, right? And the graph neural network kind of for libraries. And there's also many work and the research works try to optimize the graph access on the GPUs. And you can think of all the conventional solutions is the following 3 steps, right? You have some data, the feature vector, it's called the feature vectors of your graph, which is scattered in your memory, right? And in the memory, because of the data access of the different locations of your memory, which is very poor in terms of performance, right? So the first step is you try to coalesce all the memories, from your memories, the information you need into some contiguous kind of the location. The second step, right? You write your buffer, okay? Which you pack your data, and then you do the bulk transfer to the GPU through the DMA. Right? This is kind of the 3 steps. That's a very conventional wisdoms. Okay, everyone's using this one. Try to optimize the different ways. There's a lot of papers about this one. And but in order to understand, is that true? If I let the GPU to access the memory through the 0 copy, it is good or not? Which means you need to have a way to quantify, right, the system. Where is the bottleneck? But as I mentioned, the system interconnection is very complex. There's so many combinations, right? You have different CPUs, you have different links, etc., etc. So how do you know systematically to understand this one? So you need a tool to help you to systematically understand the different combinations, right? Are you moving smaller batches of your data or your bigger batch of data? Are you using different mechanisms or different configurations? There's so many possibilities. That's what I mean. You have to design a system. So here it shows the kind of all kinds of combinations. So because of this one, we have to design our own tools. So we designed a tool called the ComScope. This is a paper we published a few years ago. This is a tool that can give me any system, server systems, right, with the configurations. I can systematically characterize your systems, based on all the configurations of the server systems, right, in terms of the links, in terms of the package sizes, in terms of the different ways of moving data between the CPU memory to the GPU memory, for example, right? So we try to codify the best practices, the setup of the configurations and do the benchmarking, right? Do the measurement to get the performance. Once you have the performance, and we can do the plotting analysis, right? And this tool is open sourced. So we publish this open source tool, and we also use these tools to understand the workload for ourselves. And we use these tools, try to understand, given a server computing infrastructure, where is the bottleneck, right? This can help me to do the workload optimization. And so now let me show you some quick examples, data, right? This is from our tools, because our tool is automatically do this kind of categorization. So now I can show all kinds of combinations across different systems, right? So whatever the observation I made out of those kind of the categorization is not only for particular configuration, it's across different configurations. So the long story short is just kind of across the system, right? The main point is, actually we realized if you look at the performance categorization, 0 copy is not slower, right, at all, compared to any other ways of doing the data transfer. Right? This is all data shows. If you zoom in, for example, right, this is the gray, which shows you the 0 copy, right? And the other one is the conventional, the bulk data transfer. And the axis shows you different packet size. You can see across all the packet size, right? If you measure the bandwidth, the transfer bandwidth, 0 copy can pretty much achieve the similar kind of the transfer rate as any other type of way of doing the data transfer. And when they saturate, both saturates. Okay, so this is kind of shows from the physically, nothing seems to stop to use this particular way of transfer data. And also you look at some of the data from the current literature work, right? This is some of the graph optimization work from the academia, right? They always like, oh, your data transfer is slow because you cannot utilize, the system is not performant enough. You need a higher server system. You need a better system. If you look at their data, you realize actually for most of the workload they try to talk about, right? This one just shows you the axis. This is axis shows a different workload. The y-axis shows the achievable kind of the throughput for the workload, right? And this is the red line shows kind of the saturation point. If you are able to fully utilize based on what we talk about here, the saturation point, you can see most of the workload, you are not even able to saturate the capacity at all. So before you try to say, hey, you need a better servers, right? You have not even utilized your current server's capability at all. So that's kind of the main point. But even though we know, we still don't know how to optimize, right? Because in order for me to optimize, I need to understand why. Why the current, because they are very smart people, right? They're trying to do all kinds of optimization. Why they cannot meet the saturate the current bandwidth. So now we design a new system. So now, because in order for me to understand this kind of system underlying system, I need to have some visibilities. This unfortunately is no current system to do so. So we designed another kind of solution. So we put the FPGA into your system's PCIe, right? So now when the system during the boot up the system, okay, we let the FPGA to advertise to the system saying, hey, I'm the memory, okay? So now whenever the GPU try to access data from the host memory, right? Because it's through the PCIe switches. Now this will be redirected to the FPGA. In the FPGA, I'm doing very simple things. I'm just pretending this is kind of, you can think of the emulate the memory. My FPGA uses emulate the memory. Why? Because now I can capture all the PCIe packet requests from the accelerator. So now I can analyze the packet to see what is the packet looks like. And then I can further understand why the bandwidth cannot be saturated. So this is a system we published, okay, and just give you some results to illustrate this one, right? And because of we try to access data, you have sending different ways of accessing the data, right? And we try to capture the packets. So this is one way of capture the packet. So we realize if you access the memory this particular way, in this case, in the GPU, okay. So if you know GPU programming, that's good. If not, just pretending, okay. GPU basically you kind of a bunch of the thread you need to access computation, right? One way is you can do it every thread within a warp, right? Have a bunch of workload, right? They always access memory somehow independently. If this particular case, we call the strategic data access. Every thread will generate its own data request, which is about it is 32 byte packet size. If this is the way of your accessing data, if you measure the performance, you can only get about 4.7 gigabytes per second. You cannot saturate the memory bandwidth at all. And this is our observation. Now you can do some kind of the theoretical analysis. Now, oh, if every packet size is 30 bytes in your PCIe packets, because of this is in the PCIe 3.0, we did this experiment, right? PCIe 3.0 has some specification, which means your queue packet size is about outstanding packets can be 256. You users can do a simple calculations because we do a measurement of the runtime delay, which is 1.6 microsecond. You're using 32 bytes times the queue numbers, you can get, right? The best performance you can get is about 4.7 gigabytes per second. This is a theoretical data, which is kind of consistent with our observations as well. So which means if your workload can only generate 32 bytes kind of the packets, that's the performance you're going to get, right? If you are able to do different ways of workload, for example, like this, in this case, we call it merged and aligned access, which means all the threads within a warp inside of the GPU, if they access the memories, they're all aligned within a contiguous memories, and they're going to generate the coalesced packet request, which is 128 28 byte packets. If you only get 128 bytes packets on the PCIe link, suddenly your bandwidth, right, achievable throughput kind of increased a lot. You get about 12 gigabytes per second. And you do some back envelope computation, you can realize that's the best you can do, because the PCIe 3.0, the best you can do is physically, it's 60 gigabytes per second. But every packet have some overhead in terms of the header information. If you count the header information, which is 18 byte, you can realize, the best performance you can get is 40 gigabytes per second. And through the measurement, we get about 12 gigabytes per second. So which is almost the limit, physical limit already. So now this leaves you the optimization kind of choices, right? If your workload is only able to generate 32 bytes kind of packets, you cannot saturate the bandwidth. If you are able to get 128 bytes all the time, you can saturate. So now anything is in between, right? Depending on how you optimize your workload. So that's indeed what we did some experiment. Yes, if you have a mixture of 32 bytes and 128, that's how about what kind of a bandwidth you can to get. Okay, so that's kind of the tools you have. So now once we have these tools, we know what optimization direction which to go. And let me show you how we did this optimization, right? So this again is back to the graph optimization. We call our optimization for the emoji. This is our optimization. On the left-hand side is the conventional graph optimization, right? So if every thread, for example, in this case, every thread responding to a node and process its own neighbor list, right? This is kind of the traditional way of optimization. Because of knowing how the zero copies in the packet size looks like, we only need to do a few lines of code change. So now we let all the thread within a node to process all the edge neighbor list for particular node. A single line of change. Details is not important. Just say, hey, send a few lines of change, and this can be justified based on the current size of the graph. Most of the graph, the neighbor node is big enough, and more than the current 32 threads per watt. This kind of information, and we showed you if we just by a few lines of change. If you look at this data, right, this data shows you. Look at the left-hand side, shows you different workload. Okay, the x-axis, right? And with different ways of accessing your data, different ways of workload optimization. And the traditional one, we call the naive one, you can see you always generate the 32 bytes kind of packets. That is why it's pretty much 100% blue, right? The third one, which is our approach, within a particular workload, right? You can see the yellow. The yellow is the 128 byte packets. Now you can see through some of the simple optimizations, I can generate much more 128 byte kind of the packets request. In that case, on the right-hand side, it shows you, if you're able to generate more of this 128 byte, your throughput is much better than compared to the traditional one, 32 bytes. This kind of shows you this is a benefit. And of course, you apply these techniques, now you do the measurement, across different workload, and you can see indeed, and we can get a much better performance compared to the other work. Okay, so this kind of shows you how you can utilize, make every bit of the bandwidth count, right? And now we know these capabilities, now we know these optimizations, and then we put this back to the community. So we work with the DGL, like a PyTorch DGL, like a graph neural network libraries. So we wrap this optimization into our libraries, okay? And we work with the DGL teams, and now this capability has been integrated into the DGL's graph neural network, the PyTorch, right? With a simple abstraction called the unified tensor. So which means the programmer does not need to know, just utilize our tensors. And this tensor will do this data transfer for you, will generate this optimized packet size. And then so you can utilize the bandwidth much better. And has been already public made an announcement, right? It's a part of the DGL, PyTorch DGL. And if you utilize this new approach, and we also did this benchmarking, right? For the graph neural network training, and we can improve the performance, and by almost 50 times, and also for different GPUs, we can get even better performance. So the numbers is not important, that's kind of the main message, right? Shows you this is available and this is possible. So this is the first kind of example, okay? So let me quickly show you the second example, okay? And how I'm applying the same kind of principles, right? And for a different type of system optimization, okay? So in this case, is try to optimize the GPU's memory, okay? And so we all know, right? The GPU's memories is kind of limited. And that's why I mean, a lot of the workload, you cannot fit into GPU memories. Or that's why NVIDIA's try to increase the memory size of the GPUs, right? Which makes GPU even more expensive. And that's why the system kind of is kind of right now is I would call it suboptimal. But if we utilize this same principle, as I mentioned, you know, how do we make every bit count? We can design a better system, subsystem, like a memory system, even for GPUs. So let me kind of give a little bit of a review here, right? So this is the current way of people utilize your GPU, right? You have the CPU, you through the PCIe, you have the GPU, right? And the CPU has its own memory, right? And the GPU has its own memory inside of the GPU, right? Whatever the size, right? And for other type of data, the bigger data, even the CPU memory is not enough. Typical system, right? The CPU memories, the server memory you have is about terabyte, right? Maybe 4 terabytes, whatever, you know, memory is very expensive. The DRAM is very expensive, right? And the other one, cheaper one is the SSD, which is 100 terabytes, right? And also put into this PCIe. And the memory bandwidth to the CPU is much higher, right? More than 100 gigabytes per second. The SSD is much slower, which is about 6 to 8 gigabytes per second. But the SSD can have multiple channels, which you can put many SSDs. The SSD is relatively cheaper compared to the memory. So in the current server systems, right, use SSDs, which means most of your data is into the SSD. Okay. So now how are you going to orchestrate the data, right? In order for you to accelerate your GPU AI workload. So what you do is use the CPU to orchestrate all the data movement, right? The way you do the orchestration is you partition your data. For example, your data is residing on SSD. What do you do? The CPU do the work, right? So you move your data, you tie your data. Hey, which part of the data I need to use? I move the data from the SSD to my CPU memory, right? Inside of the CPU memory, I say, okay, which data do I need to use right now for the GPU? I also do another partition, right? So called a tiling. And then I move this data to the GPU. And then the GPU cranking the data, right, to the computation. This is kind of the very typical way, right? Even though you may not work on this level of details, the underlying, that's how it works, the system, right? And the TensorFlow or the PyTorch, they kind of hide all of these details from you. But that's what it happens. This kind of, as you can see, this data movement, right, has a lot of the I/O amplification, meaning because of the, for example, like the data is sparse, right? Like even though you need a piece of small data, you bring the whole pack of data, right? You do one computation, you discard it, you get another one. So this wastes a lot of the data movement, right? Which is consumes more power, right? And it makes things more expensive to maintain, right? So this is kind of one of the issues. And sometimes, you know, and for easy of programming, right? Sometimes you really want to have this unified address to address all the data you have, which is almost impossible given the current way of the system works. Okay. Now you can also say, hey, you just mentioned that this is kind of on-demand access, right? So you can access this data, you know, maybe there's also other people say, oh, I can let the GPU access the data, which of course, there's also some of other people's work, you know, even NVIDIA's UVM, right? And also some of the academic work like GPU-FS. So the GPU can access the data, but the GPU asks the CPUs to help, right? Say, hey, the GPUs can access the data, but let the CPU to help me to move the data from the SSD instead of going to the memories to my GPU. For example, it's possible, but the current solution is a lot of overhead because now the CPU also need to participate in orchestration, right? And oftentimes, as I mentioned to you, the CPU cannot even fully saturate the bandwidth, right? And then you may also say, oh, you just mentioned about the previous work. You can say, hey, this is zero copy. It's a great work, right? Why don't you apply this one? Yes, zero copy can work too. But zero copy also means I still have to move the data from the SSD to my memory, right? Then I let the GPU to access the data from the memory. So which means if I need data is big, I need to have a big memories too, which is also very expensive. As I mentioned, DRAM is quite expensive, right? So this is also not a very good proposition, okay? And also the CPU need to actually move the data from the SSD to the CPU from the very beginning. This is initialization overhead. So now, what would be the ideal solution, right? So the ideal solution would be the following, right? We call the BAM. And so we let the GPU access the SSD data directly, right? Because I know the data here, if I'm able to make every bit of the bandwidth count, the SSD for one channel able to get the 6 to 8 gigabytes. Okay, pretending if I can, right? And I also know I can put the multiple channels of SSDs into the system as well. So now aggregate bandwidth is pretty high, right? And now if I'm able to do so, then which means I can really fully utilize the data in the SSD and allow the GPU to access it directly. So now the question is, how can I make this happen? Make this easy for programmers to use such as kind of capabilities. And this paper was published this year's S+ as well. Okay. So let me just give you a high level how we do it, right? So of course, first you need to have the GPU. So we need to have, inside of the GPU, you need to have some kind of abstractions. Okay. The first one is, okay, you need to have some kind of the request because we need to generate, remember for a second, I need to generate the packet, right? In a way which is coalesced. So this inside of this one, we have some kind of the IO queues. And so this will, through the IO queues, enable me to access the data SSD directly. And there's a way for me to decide how big the queue should look like. And I'm not going to, there's some of the math behind it. I'm not kind of, in the intro time, I'm going to skip it. Just kind of through some of this back of the envelope computation. And I can compute, given the systems, given the bandwidth from the SSDs, right? Given the kind of packet size I need to generate. And I can compute, what kind of the queue size I need to have. So in this case, the 500 is reasonable numbers given the how many SSDs I can sustain the bandwidth. Okay, so this is some of the back of the envelope computation. Just trust me, it works. So once you have this SSD kind of the queue, right, and then you can write your own kind of the software. How do you manage the data cache? Okay, and once you have the cache, then you provide another programming abstractions for the programmers to use. So that for the program perspective, the GPU programmers, right, they will just assume you have an infinite amount of the memories. Okay, let me manage data access for you. And this is kind of how it works. If that's the case, if we make this happen, then the GPU can directly access data through the SSD. Okay. And let me show you walk you through this process, right? From the GPU side, in the CUDA programming, you have the thread, you allocate your data, just very simple abstraction. It's an array. You have the index to the data. And now our software kicks in, right? Whenever you access your data, you will check, right? You calculate what's the offset. If the offset is inside of your GPU memories, it's a hit, you can return your data. If it is not a hit, you will generate an IO request and put into the queue, right? And that particular thread will be kind of on hold, right? And then you do other computations. This is typical for the GPU. And then you just accumulate this IO request, right? Once the IO request kind of get coalesced, the packet size is kind of the right packet size. You submit this request into the queue, and this queue rings the bell, right? On the SSD side. On the SSD side, there's a storage controller. They're always waiting for the doorbell, right? Somebody's asking me for the job. Once the doorbell, I got the doorbell, the ring of the doorbell, and then I will start reading the request from the queue. And then I can process the request, prepare the data. I can use the DMA, write the data back to the GPU. Okay. And then the GPU can constantly polling the data. Is data ready or not? If it's ready, now I can clear up the data request queue, and then put the data back into the cache, and the thread can continue to work, right? So from the programming perspective, it's very simple. On the average, just access the data. If data is available, it's available. It's not available, I wait until the data is available. Because of the way I just showed you, right? If I'm able to generate the right packet size, I can saturate any bandwidth, right? So now even in this case, I can still, for the SSD, I can also saturate all the SSD's bandwidth, which means I can get the data as better as I could for the given infrastructure. Okay, so now we did this prototype, right? So we bought out the PCIe switch chassis, and we put this 10 SSDs inside of the systems, right? And we did the prototype and showed this result. Okay, it works. For the, as you can see here, right? On the left-hand side shows one of examples. If I'm generating the 4 kilobyte kind of access all the time, the packet, and this shows you the bandwidth, right? As you can see, if you are able to generate a bigger packet request from the programming side, you can coalesce your request into 4 kilobytes kind of a packet request. You only need the 4 SSDs to saturate your PCIe bandwidth, right? If your packet size is smaller, in this case, like 512 bytes, and your packet size, you can see you need about 10 SSDs, aggregate bandwidth, in order to saturate the PCIe bandwidth. And that's the best you can do in a given system anyway. So this kind of shows you, right, the BAMs with our solutions, we can saturate the PCIe bandwidth and easily, even with SSD, which is slow access and the cheaper memory storage. So in a summary, right, using these systems, using other BAM systems, we are able to improve the GPU's effective memory capacity by 10 to 100 times, which is much lower cost. Okay, and we can reduce the I/O amplification and 3 to 4 times, and end-to-end performance can be 5 times. And this is, of course, it's much cheaper solutions compared to keep adding the DRAMs into the GPUs or into the systems. Okay, so this is kind of the 2 examples. So let me summarize the key takeaways for the workload acceleration for a given infrastructure, right? Is this a guiding principle, right? Let's make every bit of the bandwidth count. And in order for you to do so, right, you need to make sure you need better tools so you can observe, right? Understand the bandwidth issues in the system. And then you design your novel algorithm system optimizations. So really, that's the key message. Okay. So now I've showed you my secret sauce, right? So that's up to you. What other things you can do with this? I call it new. I don't know if it's new. Maybe it's people knows about it, but hopefully, kind of I made it clear to you. So you try to utilize it, right? This is a new design principle, and now the rest is on you to see how can you design better systems, better workload optimization. Thank you. And this is I want to thanks my collaborators, long-term collaborator, Professor Wenmei Hu, and his wonderful students. And this is a lot of this is all joint work with Wenmei's and his group. Thank you. Any questions? Yes, please.
From an industry point of view, is there any particular workloads that you think that can be targeted for leveraging the work that your team has done?
Yeah, I think all of this workload, right? Like all the AI workloads, be the graph neural network. The first work I showed you is the graph neural network, right? And also including the graph algorithms, right? Like a graph traversals, right? And the triangle countings and those kind of all type of graph, bigger graph analytics can benefit from this work, which is now part of even the PyTorch libraries, right? And people can get some benefit. Okay, and this, if you want to be simple, you can use the way libraries we provided, and or if you want the details, of course, then this need to go to next levels. And this is the second piece of work, which you can benefit any GPU workload, so long as you are able to generate that kind of many requests, right? So this is I would say this solution is not specific for a particular workload. This is a general optimization principles.
Second question: you're showing the band, right? If you go a little further behind, where you had let's say 4K workload with 4 SSDs.
This one, right?
So here, you had the GPU bandwidth was 32 gigabytes. I think it's in the previous slide when you had the first band slide, right? 32 gigabytes with 4 SSDs, assuming 8 gigabytes throughput that you can get out of it. How's that? What I'm not able to grasp, maybe you can enlighten me here, is we are still limited to the 32 gig capability, bandwidth capability of the GPU, right? while the memory is still, hundreds of gigabytes or even higher.
I think this is kind of back to here. You have to do some kind of a back envelope computation, given a particular system you have,
Yeah.
right? And what type of the bandwidth you have. So this is really some of the computations, and we can go over later. Like here, right? So this is kind of this is some of the system link is given to you, right? If you are able to saturate the PCIe switches, for example, right, the 32 gigabyte per second.
Mhm.
If you are able to saturate that bandwidth, it doesn't matter how many more memory you put in. It doesn't matter how many SSD you put in. It doesn't matter because that's the bottleneck. So the way I'm showing you, how many of SSDs I can saturate that bandwidth already. If I'm able to saturate that bandwidth, that's the physical limit.
Okay, that makes sense.
That's why I'm saying make every bit count. That's why I mean, if every bit is counted, that's the best I can do.
Right.
If you really want to get more, then that's the point. You need to say, hey, let me upgrade my systems.
Knowing 32 gig is a limitation, why bother investing in memory when you can leverage
Exactly.
SSDs effectively?
Exactly. That's the point. Yes.
Yeah, makes sense. Thank you.
Okay, thank you. Any others?
I probably missed this, but in adding to this question, so you're trying to maximize the bandwidth. Did that result in a deterioration in the compute throughput?
No. That's what I'm saying. You make the very first get band kind of the computation, right? And if you're able to saturate the bandwidth, that's the best you can do. Whatever the computation resource you can utilize, there's no way I can pump even more data. Right?
One thing, you're doing a late fetch, right? So you're different fetches until you fill up the buffer. Okay.
Right.
So aren't you wasting some cycles?
This unavoidable. Because what else can you do? Because there's no more data for you to crunch the data anyway. Right? So of course, during the design of algorithms, you still have to, you have some other data, which means kind of like current GPU, right? So if some of the data that kind of get stored, right, that will be swapped out, and the GPU can move quickly to kind of launch another kind of thread blocks, right, to do the computation. Right, you work on other data. That's how you kind of hide some of this latency.
So what you're saying is that if there's a workload where you can predict what is the next fetch that you have to do, so you can start that fetch even before your computer is finished.
Right. This is a predictor for the fetch, right? It's kind of orthogonal to what I'm talking about. I mean, that happens already, that happens orthogonal to what I'm talking about here. Okay. So what I'm saying, okay, even the programming model, how are you going to access the data? The older ones, I mentioned there's a few of the ways of this kind of the slide I'm showing you, right? The different ways of getting the data from the SSD or from the memory to the GPU. This is orthogonal to whatever is a prediction. Okay. Yeah.
I just remembered that my other question is, do you see any probabilities of creating hotspots based on how data is organized within the SSDs itself? Like, or is there anything that is happening to within the logic itself to ensure that data is also organized evenly within the SSDs? Meaning, like, if I have a huge chunk of data sitting in 2 SSD, I'm still
this is another level of optimization. I know what you're saying, right? Like here, and this is a kind of orthogonal optimization here, right? So my data access. I'm using this one to give an example. Let me see which one. Okay, here. There's a whole flow here. Let me just put it here. Right. So how the SSD, right, access the data, you can do optimization. That's your data layout inside of the SSD. You can still do optimization. If you have this optimization in the SSD layout, this aggregated way of how fast you can prepare the data, so you can bulk transfer data from the SSD to the GPU, right? If you can reduce this kind of the latency, of course you can also further improve the let's say throughput, right? And this is another level of optimization. Maybe if you're able to reduce this delay latency, maybe only 2 or 3 SSDs can saturate your bandwidth.
Is there any thought process on what
What could be done? Yeah, this is
suggestions on what could be done on the data side to organize them better on the.
Oh yeah, we have some other work, right? Basically, kind of inside of the SSD. Now you know how inside of the SSD, how you do the data layout, right? So that's relate some of the for example, like a prediction. If you know some of the workload predictions, now if you're in your layout the data, for example, you already organize your data in the SSD side, right? You kind of made it more ready, for example. So now my SSD can get the request, prepare the data faster, and pump the data back. If I'm able to do so, right, I only need maybe 2 or 3 SSDs to saturate the bandwidth. I don't need 4, or I don't need 10. The result I'm showing here, right, is for didn't do much of this SSD layout optimization. Just keep assuming your data is as is, laid out on your SSDs. That's kind of show you, yes, even this kind of packet size, you need to have 4, right? Or in this case, you need to have 10. That's kind of little bit of additional dimension for you to the optimization. But no matter how you do the optimization, the physical limit, the saturation point is the same.
Any example from your side itself that you ran before and after an analogy and saw the benefit and is very quantifiable in computation if you saw?
Oh yeah, that's and finally we showed this. I didn't show in the slides here in the paper. We have the results to show like my conclusion slides showed here, right? For example, like this is also the end-to-end result. Improve end-to-end performance by how many times? So this is the benefit. This, of course, what type end-to-end means like I need to have workload, right? We tried as a graph analytics, and you can try many other workloads, like others as well.
So from an industry point of view, if we leverage PyTorch and we will be automatically in audio libraries.
No. So right now, this is 2 pieces of work. The first work about the utilize the data for the graph neural network training. That part has been integrated into the PyTorch DGL library. That one, you can if you do the graph neural network training, right? If you use the PyTorch DGL libraries, you will get the benefit. Utilize the libraries we published with the DGL team, right? But for this one, this is still a research prototype, and NVIDIA and now Professor Wenmei Hu and my collaborator, he is the senior research scientist in the NVIDIA now, and he and his students joined NVIDIA and try to. I'm speculating here. I don't know what the NVIDIA strategy. I'm just saying, hey, this is still a research prototype. Okay, we did this work in the university setting, kind of. We did this a prototype, right? Anyone interested in maybe Google or maybe CVS or I don't know. You can take this one, right? You can, and we can do the investment. Yeah, sure. Okay.
When I stand up, that means it's time to stop. And you can feel free to take a discussion outside because we are running late. So 10 minutes late. Thank you, Dr. Xiong. Very amazing talk.
Okay, thank you.
Thank you so much.